Okay, grade 12, electric currents and circuits unit test. This one was a bit of a challenge for us. And likewise, it should be because it takes a lot of practice doing problems to get used to applying some of this. It's very conceptual electrical currents. So the first question, like all units, we have to memorize some certain terms. They're all bolded in your text. And electrical resistance, the easiest way to measure it is to measure the ratio of the potential applied across a conductor and the current going through it. So if I measured that ratio is my resistance. Now that resistance is for a fixed temperature. If I change the temperature, I'm going to change the resistance. A lot of you talked about the impedance to flow, which is okay, but you have to say at constant temperature, it's easier to just apply Ohm's law in your explanation. So try to practice that. Next question comes from the text, a very obscure formula on calculating the current based on something called drift speed, how the electrons move around in a conductor. And every material has a different density of electrons in free space. So they'd have to give you that, and that is the N in terms of cubic meters. So current is equal to that density times the cross-sectional area times the speed times the charge that's going through it. So if you plugged all those numbers in, you would get a velocity of 7.96 times 10 to the minus 4. All right. A student uses the same material in question 2, but increases the diameter. And how will that affect the current? If you increase the diameter, I'll use this formula to explain it. If I increase the diameter, I'm increasing the cross-sectional area, and that's inversely proportional. So my resistance is going to go down. If my resistance goes down, my current goes up. So an increase in area, increase in current, because I have more lanes for the charges to flow through a conductor. Okay. Last little question. These should be very basic questions for you to solve because it's just plugging numbers into formulas. This is just using that resistivity formula to calculate the resistivity. Where some of you had some problems was calculating area, pi r squared. I gave you diameter. You have to convert that into the radius, and you have to be able to convert millimeters into meters. Okay, so some of us had problems with that. Once you calculated your cross-sectional area, you then multiply by the resistance, which you would have to calculate by voltage and current. A lot of you did that. Okay, and then divide it by the length and you'll get the appropriate resistivity. Pay attention to the units. A lot of you guys put the wrong units in or didn't put units at all. You would lose a mark on the IBA exam for that. Okay, here's a graph of a typical filament lamp, current, the IV graph, current voltage graph. And it's telling us that this is a non-ohmic conductor because it's non-linear. And for questions like this, when they want you to calculate the resistance, you just have to read the graph. At 4 volts, the current is 16 times 10 to the minus 3. Be very careful to make sure you look at that. And then if you divided it, you would get 250 ohms. Okay, so that ratio there would give you 250 ohms. All right, now the reason it's not linear is because, yes, tungsten filaments are non-ohmic conductors. When electricity runs through them at a particular voltage, they start to heat up and they produce light. So some of the energy goes to producing heat and light. Okay, here is a really basic circuit, and I was trying to get you to calculate the power of that bulb, but I tricked you guys a little bit by giving you internal resistance in the battery. So you were given the EMF of the battery, you were given the internal resistance of the battery, and they're asking you to calculate the power. So this required that you understood this formula and you understood these formulas. Okay, so first of all, the EMF of the battery, the theoretical electrochemical voltage in there is 1.5 volts. Okay, V is the voltage, if I put a voltmeter out here, the voltage I'd get across that light bulb. And I, little r, is the amount of energy that would be lost inside, or the potential that would be lost inside of the battery due to internal resistance. So if I would plug these numbers in, 1.5 minus the potential lost inside the battery would give me my V external. 1 volt is my potential external. And the current going through there is 1 ampere, as it says over here. Then the resistance of that light bulb is going to be 1 ohm. With all these values, I could choose whatever formula I want to calculate the power. It could be IV, 1 ampere, 1 volt, or it can be 1 squared divided by, or 1 squared times 1 ohm would give me 1 watt. So this light bulb is a 1 watt light bulb. Okay, which one of the following shows a correct circuit to use an ideal voltmeter and ammeter for measuring an IV curve? Okay, well, I want to be able to measure the voltage across the lamp, so I have to be parallel. And I want to measure the current going through there. So I can either have an ammeter here or an ammeter in that branch telling me the current that's going through there, just through this component. So B is the correct answer. This one, you just had to recognize you had to add the energy, internal and external, to get the total energy of the battery divided by the charge would give me my voltage. And this one, rather simple, you just had to apply V equals IR to calculate the voltage at each resistor. So if I know the current and I know the resistance, if I multiply them together, that'll tell me the potential difference that is being used up there. Okay, so 20 volts, 20 volts. Now this is a parallel branch. If I distill it into a single resistor, I would apply this formula. 1 over 10 plus 1 over 10 is equal to 1 over R total. Okay, that means that 5 ohms is the total of this component. So 2 amperes times 5 ohms is going to give me 10 volts. So the total potential difference in this circuit is 20 plus 20 plus 10, which is 50 volts. Okay, this is a challenge problem. I didn't go through all the steps. I just set up the identities. And then you have to practice using these 3 identities to substitute one formula into the other so you can sequentially solve each of these unknown currents. Okay, this problem is only asking us for the current in the middle. Okay, so how do you set it up? You draw the current of loop 1, you draw the current of loop 2, and you set up these 3 identities. The current going into that junction is equal to the current coming out. So I1 plus I2 is equal to I3. And then all of those 28 volts have to be used up in each of these loops. Okay, so as we go through that loop, 28 volts is equal to all that. 7 volts is equal to all that. Okay, and I have that written over here. And you probably can substitute. Often you'd have to identify. So for example, I2 is equal to I3 minus I1. So I could substitute that relationship in here and be able to create a relationship where I3 is equal to something in terms of I1, and then I'd be able to solve for I1. In this case, we want to solve for I3, so then I probably would say I1 is equal to something, and I could substitute I1 for an I3 value in there, and then be able to rearrange it and solve for I3. So you have to substitute a couple times to be able to get the answer, which was 4 amperes. Okay, the last 2 questions. This is a very classic question, electric water heater. We did it last year. Remember, electrical power times time gives you the total amount of heat energy that goes into a device. We're going to be working on this next unit. So power times time is equal to Q, which is going to be equal to MC delta T if that Q is used to heat stuff. So if I rearrange this formula, MC delta T divided by P, and P in this case can be V squared over R. I have my voltage, I have my resistance. I can then plug all the numbers in and get an answer. So it would take 1,385 seconds to change the temperature of 40 liters of water by 40 degrees. Okay, now pay attention here. All right, 40 liters is equal to 40 kilograms, which I converted into grams, 40,000 grams, because it takes 4.19 joules of energy per gram degree Celsius. So I had to make that conversion. Some of you guys made mistakes there. Okay, and then the last one is a potential divider circuit where you basically apply this relationship. The potential out is equal to the total potential of the circuit times that ratio. The resistance of that component, that fractional resistance, over the total resistance times that will give me what I get out. Now, because the resistance of a resistor depends on the length, it's directly proportional to the length, as I say over here. If I only go 3/5 of the length, then I'm going to get 3/5 of the total resistance over here. So 3/5 times 220 volts gives me 132 volts coming out. And that's it. That's the basics behind this exam. Areas that we need to work on, definitely you should do 3 or 4 of these problems, but recognize that these problems take about 10-15 minutes. So you want to leave them to the end of your exam. This problem you need to go over and make sure you know for the next unit because we use it all the time in the next unit. And this problem is just easy peasy once you remember this formula. Okay, that's it.